All right, so this is our first example involving an optimization problem from section 4.3 for Math 1560, Calculus 1 at U of L for fall 2017. So here's a sort of straightforward example just involving numbers, right? So nothing where we're attempting to attach any kind of applied context, simply optimize a certain quantity involving a number. So what do we want here? Okay, so we want a positive number. Okay, positive number. Let's call this number x. What do we want this number x to do? We want the sum of the number and its reciprocal to be as small as possible. Okay, so let's say s for sum. What is s? It's the sum of the number. There's the number and the reciprocal. There it is, 1 over x is the reciprocal for x, right? Reciprocal means you do 1 over that number. And what's our domain? X bigger than 0, right? So in other words, x could be anywhere from 0 to infinity. And so this time we don't have a closed interval for our domain, and so we're going to have to exercise a little bit of caution when we go looking for, in this case, what are we looking for? Well, we want this sum to be as small as possible, so we're looking for a minimum. Okay. All right. So one of the things that we might note, right? We might note is that s goes to infinity as x approaches 0 from the right, and as x approaches infinity, right? So the value is really big if we approach 0, if we approach infinity. So if the minimum has to be somewhere in between, right? So it's always worth looking at, if you don't have a closed interval, you don't have endpoints to check, it's still worth looking at what the behavior is if you approach either end of your domain. And we can see that as we approach either end of our domain, the values are getting really big, and we want to make the values small, and that means we need to go looking for critical numbers, right? We want that minimum to happen at a local minimum. So how do we calculate that minimum? Well, we need to take the derivative, set it equal to 0, right? S is already a function of a single variable. There are no constraints that we need to apply. So we calculate the derivative, ds dx. Okay, so the derivative of x is just 1. The derivative of 1 over x is minus 1 over x squared. As usual, if we're looking for critical numbers, we should get a common denominator. So multiply 1, top and bottom, by x squared, and then we should factor, right? X minus 1, x plus 1 over x squared. Okay, and so we can see that since x has to be bigger than 0, right? There are two critical numbers there, plus or minus 1, but one of those isn't really a critical number because our applied domain in this problem is x bigger than 0. We're not looking at x less than 0. So for x less than 0, the only critical number is when x equals 1. Okay, and one of the things that we should do, because we don't have a closed interval, because we're not guaranteed a minimum, we should make sure that this minimum, or that this critical number really is a minimum. Okay, so let's check. Okay, we're going to check. And you've got two options if you're going to check this critical number to see if it's a min. One is the first derivative test. So if we do the first derivative test, then we draw our number line. But this time, right, our domain starts at 0. We just have this one critical number at 1. And we can see that, so this is the sign diagram for the derivative, right, for ds dx. And we can see that if x is positive, ds dx, or if x is bigger than 1, ds dx is positive. If it's between 0 and 1, ds dx is negative, and so we do see that we're going from decreasing to increasing, so we have a min. The other option we could have is we could do the second derivative test. So we could calculate the second derivative, d squared s dx squared, and we get, well, the derivative of 1, right? This derivative is just 0. This is minus x to the minus 2, so if we apply power rule, minus 1 times minus 2, we get plus 2, x to the minus 3. We get 2 over x cubed for the second derivative, which is bigger than 0, right? And so that means that, so the second derivative is positive everywhere for x bigger than 0. And that means that our graph is concave up everywhere, right? And so if we have that minimum at 1, right, that critical number at 1 must be a local min, and also the global min, right? Because we can see that between 0 and 1 it's decreasing, from 1 to infinity it's increasing. There aren't any other critical points. We've got our only possible value. Okay, and so with that analysis we can come back and we can say that our number is x equals 1, right? That's our conclusion, right? It asked for the number, it didn't ask for the sum. If it had asked for the sum, we'd plug that back into S and we get that the smallest possible sum would be 2. Alright, so that's our first example. We'll move on to something slightly more complicated in the second example.